section 10.5 or lesson 10.5 here of chapter 10, we are going to get into a new base and also talk about natural logarithms, and that is base E. We're going to kind of lead into what base E is here with some compound interest stuff. This is the general formula for compound interest here. A, which is the final amount, equals P, which is the initial amount you put in, and then R is the interest rate as a decimal, so it's 1 plus R over N. N is the number of times the interest is going to be compounded per year, and then 1 plus R over N is in parentheses, and then it's to the NT power. T is the time in years, so N, the number of times it's compounded, times T, how many years. Okay, so that's what things stand for in that formula. Now we have a table we're going to fill in here, which kind of leads us into this base E. Here's the problem. Assume that you invest $1 for 1 year at a rate of 100%. So P equals 1, okay, R equals 1, and T equals 1. R would be 100%, 1 if you change that to a decimal, 1.00. Substituting them into the formula, we get this. So if P is 1, if this initial P right here is 1, there's nothing out in front here, but it's 1 plus 1 over N to the power of N. And that's what we're going to do here, where N is the number of times, so compound interest. So we're going to look at when N changes here, what these dollar amounts are. Annually means 1 time a year. So let's put 1 plus 1 over 1 in parentheses to the first power. Well, this right here is 1 plus 1, so this would be 2. If it's semi-annually, that means it's compounded twice a year, so N is 2. Right here, N is 2. Notice we put a 2 on the bottom down here. We put a 2 up there for the N's here. So it's 1 plus 1 and 1 plus a half to the second power. So that's 1 and a half or 1.5 to the second power, which is 2.25. And then we fill in when N is 4, it's 1 plus 1 over 4 to the fourth. And you could take the calculator. I'm not going to pull mine up here to do this, but that'd be 1.25 squared. It would be 2.44, and I'm going to go to a couple decimal places. There's more digits after that, but I'm going to kind of round off here. If it was monthly, that means it would be 12 times a year. So it's 1 plus 1 over 12 to the 12th power. And if you actually do 1 divided by 12 plus 1, take that to the 12th power, you get about 2.613, and there's some other numbers after that. Weekly, there's 52 weeks in a year, so N would be 52. So it's 1 plus 1 over 52 to the 52nd power. So I'll do 1 divided by 52 plus 1 on the calculator equals to the 52nd power. You should get about 2.6925, and there's some other numbers there. So almost 2.7. Daily, 365 days in a year. So it's 1 plus 1 over 365 to the 365th power. And again, you could use a calculator to figure this out, but it'd be 2.7146 and some other numbers after that. Hourly, there's 365 days. Multiply that by 24, so that's 8,760 if you take 365 times 24 hours in a day. So it's 1 plus 1 over 8760 to the 8760 power. It's 2.7181 dot dot dot. And let's slide this down. Every minute, here's how many minutes are in a year. And we'd continue here, and we're getting to some pretty big numbers here, so I'm not even going to write this down, but it'd be 1 plus 1 over that 525,600 to that power, and you get about 2.7182. As you can see, the increments in between values we get here are getting smaller and smaller. And if you actually did every second, there's how many seconds are in a year. Calculate all that out, you get about 2.7182 dot dot dot. All right. So let's take a look. This number that we're getting to right down here Let's go to the next page. If n continue to increase even larger, meaning you compound it continuously, the dollar value would approach this number e, or this base e that we're going to be talking about. This is actually base e to what, about 11 or 12 decimal places there. This is an irrational number. There's no repeats of decimals or anything, so it's approximately 2.72. E is the second most common irrational number. Irrational means a decimal doesn't repeat in digits and goes on forever, next to our most famous one that you've used for equations of circles and things like that. Not equations of circles, but finding area of circles and circumference of circles. The one you're most familiar with is pi, 3.14, and so on and so on and so on. Okay, this is this base e. The number e is referred to, it's called the natural number. So an exponent function with e as your growth factor is known as a natural exponent function. Anything where we're dealing with base e is the natural exponent function. Now, blank is a logarithm with base b being the number e. So in other words, e is going to be the base. So if we look over here, here's the abbreviation, the log. Notice the little base down here is e. Here's how we abbreviate that, and it is ln of x. ln stands for what's called the natural log. The natural log. And we use an ln, so it's kind of the letters backwards, but ln, and we'll talk about some buttons on the calculator here in a second. In fact, we're going to use that next here, so let me pull up my calculator. Approximate the following to 4 decimal places. So let's pull up our calculator here. We've got the first one. Being e to the 0.5 power. Now, I want you to look right down here. Above there's your ln key, and above it is the e to the x. So we're just going to use that button. So if we go to that button, and we go second e, and let's make that large screen, and we want e to the 0.5 power, so I'm going to put 0.5 in parentheses. So we're taking that 2.71 whatever number to that power, and let's go to about 4 decimal places like we've been doing with logs here. And so it is approximately, whoops, approximately 1.6487. Now let's take e to the negative 8th power. So if I go back to the calculator, I want second e to the negative 8th power. Now, please take a look at how the calculator displays this. This is very key. It's got e to the negative 4th. So this really means 3.3546 times 10 to the negative 4th. That's in scientific notation. So it's 3.354 e negative 4. I'll round that decimal off. Now that really means we take and we move the decimal point 4 places to the left. So this is really approximately 0.0003. Well, 33, but let's go ahead and round off to this. So please make sure you pay attention to that e. So that's taking that natural number e to the negative 8th power. Now we're going to do, this stands for ln, means natural log. We're going to do the natural log of 3. So if I come over here, now I'm just going to hit my ln button. I want the natural log of 3. So if we hit enter, it's 1.098 So it's approximately 1.0986. And remember, what that really means is natural log is base e. So what does that mean if we think about the logarithm stuff we've done earlier? That really means e, this is the base, to what power is equal to 3? Well, if I take e to the 1.0986 approximately, it's going to equal 3. That's really what we're doing here. Now if I do ln, or the natural log of 1/4, so let's do the ln of, oops, let's back that up and let's do 1 divided by 4. So it's negative 1.3863 rounded off. Negative 1.3863 rounded off. So that would mean e to that power is about 1/4 or 0.25. With common logs or regular logarithms, log logs, we went from exponential to logarithmic and vice versa the other way. That's what we're going to do here. So if I have e to the x equals 23, what that really means is the log in base e of 23 is equal to x. Now, we don't, when we're dealing with base e, we don't write log log. Here's the way you need to write it. ln, we usually don't put the base of e, because automatically when we write ln, that means base e. You could put it on there, but you don't really need it on there. So now you could actually figure out what the natural log of 23 is, but here we're just going from one form to the other. So this is exponential form because e is to a power. We're writing it in logarithmic form. So this one would be the ln of 6 is equal to 8 if we do a similar thing there. The ln of 6 is equal to x. Over here, now we're going the other way. Now this is natural log, so that's base e. This one's going to be, this is going to be base e also. So I'm going to take e to this exponent equals this answer right here. So e to the 1.2528 is equal to x. Now we could actually do that on our calculator, but we're just leaving it in exponential form, so that's how we're going to leave it. Over here, this would be e to the 2.25 power, so this base to this power equals, is equal to x there. Let me erase that and slide that down a little bit. I don't want that up in the exponent. So is equal to x. Okay, so that's just going from one form to the other. All right, we're also going to talk about inverses here. Base e and natural log are inverses of each other. Kind of like when you had this. If I had the log in base 5 of 5 to the third, if we think back to the logs we did earlier, okay, if this base and this matched up, that was equal to 3. They kind of canceled each other out. Or if I had 5 to the log base 5 of 4, if it's 5 to a log in that base power, that canceled out and it equals 4. Those were inverses we did with earlier logs. Well, now, e and ln here, e to the power of natural log, kind of cancel out. So it's going to leave me with 21. Here, I have the ln of e to a power. They kind of cancel out. They're inverses of each other. My answer is that power that's on e of x plus 3. Here, e to an ln of 7 power, the e and ln cancel out, it's 7. Okay, this is just recognizing inverses of each other. We're going to use this to actually solve some equations here in a little bit. Here, ln of e to the 5x minus 7, ln and e cancel out, it's just 5x minus 7. So it's recognizing inverses of each other with base e and the natural log. Okay, and they're going to be used to actually solve natural log equations where we're dealing with base e here. So here's what you want to look at. We have this first term of 3 times e to the negative 2x power and then I have plus 4 is equal to 10. What you want to do is you want to get the base e alone first, algebraically undoing things like you've done in regular equations. So first step here is to subtract 4. That gets rid of it. I have 3e to the negative 2x power equals 6. So I want to get rid of that, the term that doesn't have the e in it. Now I want to get the e alone. I have 3 times that, so my next step is I want to divide by 3. So I have e to the negative 2x power equals 6 divided by 3 is 2. Once you get down to just e to a power, and I'm trying to solve for x, now I do what's going to get me the inverse. So I do the ln of both sides. So I'm going to do the ln of that side, but I also have to do the ln of 2 on the right side. This, think about what I just did with inverses a minute ago, cancels out, leaves me with negative 2x equals the natural log of 2. Now, how would I get x alone? I undo multiplying it by negative 2, so I divide by negative 2. So on your calculator, here's what we're going to do, and I'll do this on mine. I'm going to take the natural log of 2, and I'm going to divide it by negative 2. So I'm going to take the natural log of 2. So I'll put a 2 in front, and I'll enclose that. Natural log of 2 equals, and I'm going to divide that by negative 2, and we get that answer. We're going to go to 4 decimal places, so it's about negative 0.3466. So approximately negative 0.3466. So you could check that if you plugged it back in. If I took e to that power, e to the negative 2 times that answer, multiplied it by 3, added 4, I'd get approximately 10. This one's very similar that we're going to do next. We want to get rid of the plus 5 first, so I subtract 5. So I have 2e to the negative 2x is equal to 10. I'm going to get rid of the multiplying by 2 to get my base e alone. So e to the negative 2x is equal to 5. Once you get down to this and your variable's on that power of e, now I do the natural log of both sides. This cancels out, they're inverses, so negative 2x equals the natural log of 5, and now I'm going to divide by negative 2. Very similar to the one I just did. So if we take the natural log of 5, divide by negative 2 on our calculator, so I'm going to go the natural log 5. I like to hit equals in between. I'm going to divide that by negative 2, and we're left with negative 0.8047 approximately. So approximately negative 0.8047. Okay, last two, now we're going to start with ln. So what you want to do here, if you have an ln, if the x is involved after the ln, now I want to take do the e base on both sides. So here's what I mean. I'm going to take this and put it as my power on e, and I'm going to do e to the 4th. Remember, these are inverses of each other. We just looked at that. So that leaves me with 5x equals e to the 4th. Well, now I'm going to divide by 5 to get x alone. So I'm going to take e to the 4th power and divide by 5. And we'll figure out approximately what's that equal to. So let's go with e to the 4th divided by 5. So now if I'm doing e to a power, I hit second e, and I want to the 4th power equals, and I want to divide by 5. Now I could probably do that all in one step, but I get about 10.9196. So approximately 10.9196. Okay, last one here. I'm going to do, now it's an inequality here because of that symbol, doesn't matter. Still want to do it just like an equation. So e to the ln of x minus 1 is bigger than e to the negative 2nd power. These are inverses of each other, leaves me with x minus 1. Okay, is greater than e to the negative 2nd. I want to get x alone, so I'm going to add 1. So x is bigger than e to the negative 2nd plus 1. So x is bigger than, I'm going to do this on the calculator. So if we do that, we take e to the negative 2nd equals plus 1. I won't do this one on the calculator here. You should get 1.1353. So x is bigger than that. And that's the lesson.